introduce my colleagues, Feryal and Gheorghe. They will be teaching this tutorial. It's a really amazing tutorial on reinforcement learning, and that I'm sure you will enjoy. So just logistics, please join the RL tutorial channel in Rocket Chat, and please ask all your questions there. So do not use Slido to ask questions, because we will not be looking at Slido. Ask questions in Rocket Chat. And if you need help from the TAs will be there to answer your questions in Rocket Chat. If you need help, if you want to share your screen with the TA to get help, please check the links that are on the homepage under the video stream. You will see there, get help from a TA, and there are 5 great TAs there to help you. So with this, I am going to hand over to Feryal and Gheorghe. Enjoy.
Gheorghe, do you want to go first?
Yes, hello. Hi. So my name is Gheorghe Comanici, and I'm a research scientist at DeepMind. The stuff that I work on, my experience is mostly in reinforcement learning, but lastly, I've been working on hierarchical reinforcement learning. And in a nutshell, this is the idea of working with agents that have multiple levels of abstractions over multiple, also different timescales, as opposed to just the timescale that is dictated by the environment. So this is basically what I work on, and I'm really excited to go over this tutorial today. Feryal.
Hi, everyone. I'm Feryal. I'm a research scientist at DeepMind as well, and I also work on reinforcement learning. Previously, I worked on imitation learning and sort of trying to think of ideas to make basically reinforcement learning more efficient, and also really passionate about hierarchical reinforcement learning and everything, and really excited to get a chance to talk about what we're very passionate about with you today. Great. So maybe I get started, Gheorghe, just to give some ideas of what we're covering, and then handing to Gheorghe to go through the first part of the tutorial. So I think today you've heard from Diana and Doina on fundamentals of reinforcement learning, covering sort of value-based methods and policy gradients. In this tutorial, we decided to sort of focus mainly on value-based methods, specifically tabular Q-learning and policy iteration, and then go to more function approximation and give you some ideas of how to sort of implement DQN or neuro-fitted Q iteration. So you're familiar with this loop by now, I hope. In reinforcement learning, the problem we are trying to solve is we have an agent that has a goal, which is it wants to maximize the reward it gets in the environment. And then it interacts with the environment by sending actions, and then the environment returns some observations to the agent and some rewards based on which sort of the agent sends more actions to the environment, and this loop continues. And yeah, I'm going to hand it to Gheorghe to give you some idea of value-based methods, and then we give you some details about the libraries we're going to be using. Gheorghe?
Yes, thank you, Feryal. So let me just resume the presentation on my side. Yeah, so just to reiterate on what Feryal said, the tutorial will focus mainly on value-based methods, which, as opposed to what policy-based methods are doing, is they maintain a model, or you maintain a value for every single decision that you make. So think of a decision as a pair. It's the action that I've taken at this particular state. So you maintain a value, and what this value really is, if you recall from the lectures earlier today, is this idea of adding together all the rewards that you've seen along a trajectory. So the trajectories in this tutorial will be denoted with the letter tau, the Greek letter tau. And basically what the equation is saying is we're adding these things together, but of course we're going to use this gamma value to give more importance to things that are recent versus things that happen in the future. Right, so that's basically the idea, and the one thing that makes all the value-based methods much more tractable is this super equation, the Bellman optimality equation, which basically gives a nice recursive formulation for this Q value. So essentially, it says that if you work with a method that is value-based, so if you already have an estimate of the value Q pi, whether it's exact or not, you can always try to use that to bootstrap. So you don't have to wait for the future interactions to finish. You don't have to wait for the episode to finish. And in many environments, this idea of finishing or episodes is not even true. Like you have a continual setting where things keep on happening. So if you're in that situation, basically the Bellman equation says, don't worry about it. Just try to use whatever estimate you have, and your value will still be valid. Right? So here there's two notions. So there's the Q value, which looks at the value with respect to state action pairs, so basically decisions, versus V, which is the value function of the state. So the value function of the state, it's essentially just averaging over all the actions that you can take with that policy over Q. So that's the Bellman equation, and basically all of the algorithms that we'll see today will work with this Bellman equation, and we'll try to exploit it as much as possible in different ways. So I'll hand over back to Feryal to talk a bit more about the technical aspects of how we do this with code.
Perfect. I think some people are mentioning that they see two presentations. So is this better now? I'm checking the Rocket chat, so if you can tell us if you see two presentations or one. Okay, I don't see any answers, so I'm going to continue. Okay, perfect. So in order to sort of implement these agents that we talked about, we're going to rely on a few sort of libraries that we use at DeepMind. Acme, for instance, is a library of reinforcement learning that sort of it provides you with building blocks that you can put together and build sort of complex agents as well as simple agents. Basically, this enables sort of reproducible reinforcement learning, and we are really passionate about that. And also it sort of tries to be very simple. So if you use just a single process agent, which is what we're going to be using throughout this collab, it's going to be very looking the same as if you're writing a distributed agent. So that is very useful when we're doing research and we want to also scale at the same time. And then there is Haiku, which is the neural network library, which is written for JAX. If you are familiar with TensorFlow, we had another one called Sonnet that we use in TensorFlow 1 and 2. So this is very similar. Then we have DeepMind environment, or DMN wrapper, which wraps the environment to make it sort of suitable for agents environment interaction. So if you follow in this collab, you need to install these packages. They don't come directly with the kernel that you have. Sorry, yes, I'm gonna run them as well. And this is gonna be installed in the background. Then we need to import the modules that we are using. So after your installation is complete, please sort of run this cell as well to import these modules. I'm gonna go down, just give you a very brief overview of the loop and how we are implementing each part of the loop. So we have environment and agent. For us, the environment is this grid board that you're looking at here. It's very simple for the purposes of this tutorial, but most of the methods that we're going to talk about sort of can, especially the function approximation part, can be extended to Atari or more complex domains. And yeah, in the beginning, our agent is going to be just a tabular agent. It sort of keeps a table of these Q values. And Gheorghe is going to give you intuitions about that. The environment that we're going to be using, let me go ahead and import these. The environment that we're going to be using is a grid board environment. Basically, it's very similar to this. And there is an agent that wants to reach the goal to get a sparse reward. And we have two versions of this environment, simple and obstacle. The simple one is this one. Basically, there is just an obstacle in the middle. Then there is an obstacle one, which is more complicated to go through. We are going to visualize this shortly. So if you can go through your collabs and sort of continue to this stage, that would be great. And I'm waiting for this to be installed. Gheorghe, do you want to add something, or to what I was saying?
No, I think you explained properly. I was just I forgot to start running my collab, so I was just trying to run it myself.
Perfect. Oh, I think I need to increase the fonts. Sorry. Is it better? Hopefully it is better. I'm gonna close this. So perfect. Okay, so I think my imports are done. I'm going to run the code for grid implementation. You don't need to worry about this part. This is basically a Python grid board implementation, which is useful for sort of going through this tutorial. It's quite simple, so you can maybe we documented it well that you can follow this later. Okay, and now let's visualize our grids. So this is the simple one. This is the obstacle one. As you can see, there is like this valley here which is, as Diana was mentioning, sometimes, you have a cliff, and if you bump into these walls, you're going to get negative rewards. So maybe you're less inclined to take this path if you're on policy. And we're going to check later. So I think I covered most of the things here. So in this environment, agent has 4 possible actions: going up, right, down, or left. The reward is -5 if you bump into any of these walls, which are indicated with black, and +10 for reaching the goal. And before you start any interaction, it's really useful always to look at what your environment provides in terms of action, observation, rewards, and discounts. And here we see that our actions are discrete, 4 values that we can take, and observations here are sort of a grid of shape, sort of 9 by 10 by 3, which each channel indicates 1 is for agent position, 1 hot, 1 is for where the walls are, and 1 is for where the goal is. We can get into details later. And then you have discounts, and then I'm going to reset the environment and show you sort of how it looks like in the first instance. And one other important thing is that the DM environment wrapper that we are using, when you sort of step the environment or reset the environment, you get returned an object called time step, which contains the step type, whether it's the first state of the episode, or whether it is the middle of the episode, or whether it is the last terminal state that you reach the goal, or maybe the time steps are finished for your episode, the max time step. And then you get the reward, discount, and observation. So we are going to be using this throughout the collab. And if I step the agent with action 1, which is going right, it goes right. And we can plot the state. And then, I'm going to run the run loop. This is the run loop we are going to be using later. Gheorghe, do you want to get information on this, or do you think later it's better to do?
I think if people run into trouble, we can go over it. But basically, this is the code that implements that diagram that we were talking about earlier. It's just that I think what's important to mention is that this run loop is based on the fact that the agent follows the Acme API and the environment follows the DMN API. So as long as any of these are implemented with the right API, you can just plug and play any of them, and the run loop will be the same, which is great for future use.
I'm going to zoom again. I think we had some problems with zooming. Please let me know if you want me to zoom more, because my screen is slightly bigger, so I don't understand. And thank you, Gheorghe. I think we can give more details later when I describe the agent API. So, okay, there is also the evaluation loop. It's similar to run loop, except you don't want to update during the evaluation loop. And I'm going to quickly give you the overview of agent, which is the same API of Acme agents. This is quite simple. So you have an initialization part where you're getting how many actions and state this agent has. Then you have to implement the select action, which sort of is the policy, basically a forward of the policy. And given the observation, you want to return an action. Then you have observe first and observe. So why do we have observe first? It's because the first observation that you get, the first basically time step that you get from the environment, it does not include any actions or rewards or discounts, because you're not yet interacting with the environment. You just get the first observation after reset. So it's slightly different. And observe is when you get when you sort of take an action and you want to see, and also you get the next time step and you want to do something to that observation. We are going to go through details of this when we talk about specific agents. And we talk about the step type, when it's mid or last or start. And now just to quickly show you, you can build a random agent following this API. This random agent is an Acme actor agent. It has the methods we described. Select action just returns a random policy. This random policy is just a uniform policy over the 4 actions. It selects one by random, and then observe first or observe do nothing, because this agent is random. It doesn't care about what observation it receives, and there is no update because, again, this is random. But this can be followed for any complicated agent as well in the future that we will see. And let's go ahead and run this. And now we can visualize the random agent's behavior. Quickly, you should see a video.
So Feryal, there's a very good question on Rocket on the differences between OpenAI Gym and DMN. Maybe you want to comment on that, on the fact that we actually even provide something, a good tool at the end. But
yeah, that's a good point. So Gym environment provides a series of environment that you can sort of use like Atari, or they have control tasks. DM environment is not really a bunch of tasks. It's just a wrapper on top of any environment that you could then be consistent across interacting with many different environments when you have like several agents, and you want your agent to be used for many, many different environments. You want a wrapper that is consistent, that always returns to you the timestamp, because often if you want to use different environments, they have very different ways of returning information from interactions with the environment. So we want to be consistent, but you don't have to use this DeepMind environment wrapper if you already know specifics of your environment and you just want to sort of interact with that. I hope that's clear. Let's look at the random agent. So it doesn't care about anything. It's just randomly moves, and it's quite happy about it. So yeah, perfect. So I hope, this was clear, but I'm going to answer any question on Rocket Chat now. I hand it to Gheorghe to go through the tabular agent section.
there's not much questions on the first zero part of the lab. Then maybe I can go ahead and describe a bit more the first part and the first set of exercises. So this is basically based on the idea of using tabular agents. And the word tabular, what it really means is that you can, when I mentioned the fact that we care about the Q values, tabular means we will actually have an explicit table for all these values. Right? This kind of goes counter to what you've seen up until now in the summer school, which is the idea of having an input that can have any structure and then an output that tells you the value. So tabular, it really matches a lot better the theory, and it helps us build the proper intuitions. But in practice, of course, it will rarely be the case that it's helpful. But in the case of a grid world, as you can see, the number of states is quite small. If the goal stays in the same location and the obstacles are always at the same place, then the notion of tabular agents makes sense, because you can easily create a table that has, 10 times 10, not even 100 states, right? So to make this simple, what we provided is this observation type. So the grid will support different observation types, just to make sure that we go over different methods. So the observation type that you want to have for the tabular agents is the state index, right? And essentially, if we run this and we try to if you look at the observation spec, you will see that the type of the state or the observation is really just one integer. It's nothing more complex than that. So what we'll try to cover in terms of tabular agents is the policy iteration, Sarsa, and Q-learning, which I think all three of these should have been covered in the lectures earlier today. So let me talk a bit about policy iteration, which is the first set of exercise that we'll go through. So policy iteration is this idea that we have a value that we started with a policy, could be a random policy, and what we can do is try to execute this policy multiple times to kind of get a sense of how good it is. And how good it is the V, the value function V or Q. The diagram says V, but the algorithm works with Q. But I hope you're comfortable with the fact that these two are essentially interchangeable. But the idea is you have a way to evaluate the policy, you evaluate it. Once you evaluate it, then, which is the first step, it's called policy evaluation. So I'll talk in more detail about that. But once you evaluate it, and you know how good every action is with respect to other actions, then you can improve the policy by now changing whatever you're doing in the past with an action that actually seems to have a higher value with respect to that policy. Okay? So if you just do one set of these things, the policy iteration and greedy improvement, it's not enough, because that will just give one slight improvement to the policy that was already bad. But theoretically speaking, if you keep on doing this process multiple times, you will converge to the actual best policy. And convergence is basically saying, I take the policy, I evaluate it. Once I do something greedy with respect to that evaluation, nothing changes. So if nothing changes, that means that your evaluation is telling you you're already doing the best that you could do, right? So there's nothing to change, okay? So for policy evaluation, the way we would do this is we will interact with the environment. And to do an evaluation, you don't necessarily have to use the exact same policy. So even if you have a policy that you're trying to evaluate, which is pi b, the behavior policy, pi e, the policy that you're trying to evaluate, you could use any other policy to actually evaluate it, right? And basically the algorithm gives you a way to do exactly that. Why would we use a different policy than the one that you're evaluating? Well, the reason for this is because in many cases, the policy that you're trying to evaluate might not do proper exploration, right? So since the policy that you're using as a behavior gives you access to samples that tells you how good every action is, if you have a policy that somehow goes and gets stuck into a corner, then all you'll do is you'll evaluate that particular corner. And everything else, you have no idea what's happening, right? So because of that, it's very important to actually use pi b, which is a behavior policy. That is, I would say, random, because if it's random, it actually has the chance of taking you everywhere. But we will see later in the tutorial, and probably you've seen in the lectures, but random is not always great because it might actually not advance you into interesting parts of the state space. So a combination of random with whatever you know best about the environment is probably going to be the best. But for the first exercise, we will just use random as the behavior policy. And then for policy improvement, mathematically speaking, it's as simple as once you evaluate it and you're happy with your evaluation, just take the argmax on your values, and that's going to be your next policy. Okay. So just to, I think this was kind of described a bit in terms of the agent API. What we will use is this class called Acme Actor. And for the class Acme Actor, the interaction is basically described in this diagram where you get an observation. Given that observation, there's a policy function that tells you what the action should be. Given that action, the environment responds with a reward and an observation, the next observation, and the actor will do an observe on that tuple, which we call it a time step, and we will say, okay, well, this is how I should change whatever I know about the Q value up until now. So this is basically what you will have to implement. So just to go a bit over the code, we took care of the initialization, most of it. But essentially what you will have to do is to make sure that you will return the Q values. This is good for visualization later. So you will need to store the Q values in a table, as mentioned earlier. You will have to implement the select action. So this shouldn't be too complicated because at init you have the behavior and evaluation policy. So hint, probably will have to use the behavior because select action is the behavior of the agent, right? It's basically telling us how the environment how should the environment evolve? And that's not the evaluated policy, but it's rather the behavior one. We did the observe first because it's trivial for you, but what you have to do is the observe, and then there's an update function, right? First you observe whatever's happening, you store it internally, and when the update function is called, this is when you update your Q value table with the latest function. So basically the idea is to look back to this, what you would see in a textbook. This is a textbook description of an algorithm, and try to technically fit it into this Acme agent actor interface, which will be used in the run loop to actually run the code. So I don't know if Feryal, do we want to maybe give a few minutes and answer questions along the line, and maybe create a poll to see how many people are actually either done or struggling with this? Or
yeah, that sounds great. I think maybe this time we're going to give more time for them so everyone can catch up to now. Especially I see some people have problems with installing packages. Yeah, sometimes it's good to restart your kernel. If that happens, like you can go to runtime and reset the kernel and then start again from the beginning. Perfect. But yes, at this point, if you have any questions, we're going to be reading the Rocket chat. So I see a question, Gheorghe. If I started with different random policies, will I get to the same final optimal policy in policy evaluation?
Oh, yeah, so that's a very good question. So it's actually, there's a theoretical result that says that in the tabular case, again, this is purely restricted to the tabular case, no matter your initial policy, you will always converge to the same optimal policy. And that's because that optimal policy is unique. Well, unique up to, because if you have two actions which have the same outcome, then you could randomly pick any of those two actions and have the same thing. But if you think of a greedy policy, if you think of the optimal greedy policy, you will always get the same value at least, right? Even if if there's a difference in the action, it's really because those two actions are equally perfect or equally optimal. But that's in the case of tabular. If you talk about using function approximation, which we'll see later, or if the environment is not an MDP, so you've probably seen earlier today what an MDP is, but I can tell you what an MDP is not. An MDP is not something where some information is hidden from you. So if some information is hidden from you and you don't really see everything, then doing this process, the policy iteration, will not lead to the same policies. And there's more than just one optimal policy. If anything, in many cases, it ends up being random. So being greedy in the way that we explain it here will not do the deal. So I hope that answered the question.
And yes, they're asking the convergence rates differ, right?
Yes, of course. The convergence rates differ. So if you if you start with different policies, you might have policies that the iterations that converge much faster. Like if you're really close to optimal. And I think it also depends on the environment. Like even in the tabular case, you will have experience where the environment is so simple that doing just a few iterations might actually get you to the optimal policy, versus others that will take longer. There are intricacies where you would have to find the right policy by doing a bunch of switches. There are some theoretical results onto the upper bound with upper bounds on the number of iterations that depend on the discount value, and of course the size of the action space and state space. But I don't think they're important for the current tutorial. Yeah, so there's a question about what should be used for the table. So I just point out, because you did see in recent tutorials yesterday, the idea of when you use JAX, you can use JNP to actually get things that where auto differentiation kind of works properly with. So it's just JNP is a version of NP that allows for differentiation. In the tabular case, we do no derivatives. We will do that later in the tutorial. So because of that, using just pure NP will actually make no difference. Like, you should just use NP and not worry about any JAX-related things whenever we talk about the tabular case. There's a question about tau, whether tau is a set. So tau is a sequence. It's basically, think of it as the sequence of state, action, reward, tuples that happen throughout the episode. So basically, whenever you do this, whenever we talk about formulas that are conditioned on tau, think of it as this sequence of things. Whatever happens in the environment, in the environment agent loop, is your random variable, and this is what you're kind of evaluating.
Yeah, and to add to that, I think Diana mentioned the Monte Carlo update. So if you want to do Monte Carlo update, you need the whole sequence in order to sort of compute the expected value. So so that becomes really important, that you want to sort of keep partial trajectories or full trajectories that way, which are these taus, basically.
Yeah, so the idea is that in this tutorial, we'll try to exploit the Bellman equation to avoid doing that. in Monte Carlo, whenever your agent has a call to the observe, it will actually want to store that. It will actually want to keep track of everything that happens to do proper Monte Carlo updates. But in the case of the agents that we're implementing, we're trying to avoid that. And we're just using the bootstrap values and purely look at what happens in that one time step to do our updates.
Perfect. And yes, you have solutions, by the way, in the collab, and this was intentional, just to keep it all in the same place so we can go through the tutorial and show you the results as we go forward. You don't have to look at them while you're doing the sort of exercise yourself, but if you're stuck, feel free to have a look. Then it helps you maybe for the next one to sort of build some intuition. And no worries, we are available throughout the whole summer school and Rocket Chat to answer more questions if you want to do them later as well. Yeah, great. So maybe, do you want to go through the solution now, Gheorghe, just to get us started?
Maybe we can just answer the one last question that talks about the step size. So the step size, let's go back to the textbook description of the algorithm. So basically, whenever because we are doing sample-based methods, right? In this case, we're actually sampling. We're interacting with the environment. We don't have a model, so we can't do the update as the Bellman equation actually dictates, which is an expectation. Then we have to think of this. We have to think of this as updates which are stochastic, and in this case, we want to use this notion of a step size that tells us how fast do we want to update our function. So this appears basically in this notion here, where with the Q value for a state action pair that we've observed is updated with the TDR, but we use a step function to make sure that we account for other things that could have happened. And the step function kind of does a pseudo averaging of all the samples that you see. So the behavior policy, as I mentioned before, is you could do this only with the evaluation policy. So you could use the policy that you're evaluating to actually select actions to generate samples for your updates. But that could actually run into trouble, because if ever you start with a policy that is very poor, or even in the process of doing your improvements, you end up with a policies that somehow get stuck into one place of the environment, then the samples that you get are just very, very poor. And your updates of the Q value will be biased towards that region where you get stuck, and then your algorithm might not converge. So because of that, you need a different policy, which in this case is the behavior policy. For the exercise that we run, the behavior policy is a random policy, which is somehow guaranteed to make sure that it covers everything and not just some biased part of the state space.
Exactly. And one thing to add is like Q learning methods are really nice because you don't really need the behavior policy to be exactly the policy that you're sort of evaluating. And that's nice because you can imagine you can use demonstrations or whatever, like any data from any other policy that has been sort of executed before. And then you can still learn from that. And that's really powerful. And it's very useful when, I don't know, interacting with the environment is expensive. You want to be fully off policy and like robotics. And so just keep in mind that this is a nice property of Q learning methods.
So I'll just go through the solution now, but just in the interest of advancing with the tutorial. So basically, at least the solution that we provide is to use, as suggested in the Rocket Rocket chat, to use a NumPy array for the Q value. And because it takes two inputs, the states and the actions, this will be a two-dimensional array, basically, which starts at 0. We don't know anything, so we start at 0. Whenever we're asked for those good values, we will just return the table itself. Essentially now, whenever we do observe, what do we do? So as described in the algorithm, the textbook description of the algorithm, there's this notion of a TDR, right? So to compute a TDR, we have to basically look at the Q value to generate one action with the evaluated policy. So we would know what the next action would be on the evaluated policy. And then we will we'll do this simple update that will say reward plus the gamma times the Q value of the action that was provided by the evaluation policy. This is basically the description of the Bellman equation. So we subtract the previous value that we had, and this would be our TD error. This is basically saying TD error, which is temporal difference error, into our prediction of what the Q value of that pair was. So what we do, we store this TD error. Once we are ready to update our Q value, right? When we do observe, we just store all the information that is necessary for our updates. Once we need to update our value, we will basically take the stored state in action, which were previously used in previously seen by the agent, and we do this simple update where we use the step size and the TD error to, and again, this is a plus equal, right? Where we're trying to add back to the Q value whatever the error was telling us. So if the error is positive, it means we were underestimating the quality of the action at that state. If the error is negative, we're overestimating and we have to adjust. So that's basically the solution. As I mentioned, I mean, you might have variations of this, but the idea was really to try to see what the algorithm looks like, the textbook description, and try to fit them in this API, actor API, because that makes it very easy for us to actually compare with other algorithms and see the results. So you don't have to stick with this exact version, but that's basically the solution that we have. So let me just run a bit this agent, and I also run this cell that has some helper functions for visualization. Don't worry too much about that, but it's good to have because then we can see exactly what is happening here. So once we have a solution, which is what I invite you also to do and try to get a validation of whether or not your solution is right, is to take a random policy on the simple task. The simple task is basically the task where the state, the start, and the goal are just along the same line, and there's no obstacle between the two. So we run this for 1,000 episodes, and this is basically the visualization of the Q value. This is something that you should also see. I mean, a variation of this, of course. And as you can see, the negative values are mostly around near the walls and near the obstacles. And the value functions are highest near the goal and lower far from the goal, which is what we would actually want to have. Even though this policy is, again, I think since this is the evaluation of a random policy, so even a random policy will have this value. There's nothing that says the policy is very good at actually finding the right path. Good. So this is the policy evaluation. You should see something along those lines. And then the next exercise, this should be much shorter, where we're not going to spend too much time on this, but the idea is to now implement this improvement, right? How can we now take a set of values, right? And given those values, try to implement, to return a policy that will say, oh yes, I look at the values, give me the input state and action, and I will return the actual the action that maximizes those good values for that particular state. So that's basically what policy improvement is. Okay. Feryal, are there any questions that you think would be good to address before we move on?
Yes, I think there were a few questions. Let me go back. What is behavior policy like off policy? Yeah, do you want to take that?
Yeah. So yes. So in this case, the evaluation is done off policy. So this is the notion of doing off policy evaluation, where you evaluate a policy while behaving in a different way. So for policy, for this particular task, it's possible to do that, and the algorithm itself is guaranteed to actually compute the Q value of the right Q value. So that's just saying the behavior. The behavior, it's off policy, but the updates themselves, they converge. Again, going back to the algorithms, the updates are on policy, right? So here I'm actually looking at what's the value of the next state with respect to the action that I would have taken with the evaluation policy, right? So that's the idea of, say, doing on-policy updates, right? So the behavior is off policy, but the updates themselves, or when we compute a TD error, are on policy. I hope that's not creating more confusion than it should, but it's important to see the distinction between the two, right? You could behave, you could generate actions and experience using a different policy, but whenever you do the updates, you actually are making sure that you are being on policy with respect to those updates. So the TDR is the TDR of the policy that we're trying to evaluate.
Exactly. And then there's another question: does it make sense in simple Q-learning example like this to anneal the epsilon greedy parameter as done in the QN?
Yes, for sure. So I think in this case, we're not doing that because this is kind of adding complexity to the algorithm, but pretty much, that's why we call it a step size. Anything that we know about step sizes, whenever we do gradient descent or whenever we do any kind of optimization model, kind of applies here too. And it does make sense. I don't think it would actually help too much because the examples that we have here are very simple, and that's why we're just keep it as a constant for now.
And yeah, and absolutely. And one thing is that here we are using the evaluation policy, and we want to be on policy and be greedy with respect to the update that we are making to the Q table. And we are not really updating the behavior policy, right? Because the behavior policy is that constant. In the QN, the behavior policy is exactly the policy that you're updating with some epsilon greedy parameter. And then it's good there to anneal the epsilon because in the beginning you want to be exploratory because you want to update your Q function well, and you don't know anything about the environment. But as you sort of gather experience and learn more, you want to be more conservative with respect to your Q values. And you're hoping that you already learned some good, values for the environment.
Yeah, so I think there was a question about what, it's not very clear what should be returned by these greedy Q values. So I think this function is actually used for visualization. And if you look at the visualization, basically what we would like is to print out what's the policy for every single location on the grid. And for that, we will compute greedy on a vector. So think of the Q values as being a vector, the length of the number of actions. And what we want is to basically do a greedy step on that, or the argmax. Yeah. So again, this one, it's probably a one-liner, so that's why I'm not going to spend too much time on it. But the idea is NumPy has a way of doing this. You just do the argmax, and basically the new policy is the one that you're by simply doing this argmax. Now you have a better policy, right? Now you have an improved policy that can be taken further, and now we can pass it back as the evaluation policy into the previous agent that we have, generate new trajectories with an improved policy, and repeat the process until we have something that we're happy with. So I think we'll leave this third task as an exercise, just for yourself to kind of play with it, because the idea now is that we have code that allows us to run for variations of number of steps. Of course, the more steps you run, the more data you have, and essentially you should see that your estimates are better, and hopefully even the improved policy is better. But also, if you want, you could actually take this further and run this multiple times until you get to the optimal policy, and that's the true validation that you implemented policy iteration, fully implemented policy iteration.
Gheorghe, can you run the cell where we visualize the Q values? Because some people have confusions over what that means, the subplots. That would be great.
Yes, okay. All right, so let me see if I can see the questions.
So this is the policy. Maybe we should show the Q value table.
The Q value of this policy.
The visualization, yeah.
Do we have it? Oh, yeah.
It's here. Yeah, perfect.
Yes. Yeah, so if you can see that, basically that what we visualize here, the arrow tells you the action that you would take, and because it's a greedy policy, in theory and in general, your policies are not necessarily deterministic, so it wouldn't be easy to have a visualization. But because in this case we do the argmax, this is greedy, and this tells you that already after one iteration, it seems that the agent has the optimal policy from start to goal. It doesn't have the optimal policy from everywhere, right? But because our episodes have been generated from the same initial start date, You can think of it as the policy got a lot of information around the start goal, the start state, and it was able to actually get enough information to figure out that the best way to act, at least in this left side of the environment, is to go down, all the way down. And of course, this arrows to the right means avoid the obstacles as much as possible. Yeah, and this is the visualization of the Q value, right? So again, for every action, they're slightly different because going left or right when you're near an obstacle, it really makes difference whether or not the wall will be hit or not. But they're quite similar, and as you can see, there is always much better value in being close to the goal, and much lower value if you are into areas that are. I'm sorry, here the goal was changed because I think we changed the task to obstacle. Yeah, so the goal is actually to the right side. So here the highest value is always around the goal, and the lowest value is near the obstacles. Yeah.
Yeah, and you can see that although going from the sort of that very narrow path, it's going to give it more returns because it's going to get there faster to the goal, but it avoids it because, you know, it is very, the chances of like hitting a wall is high.
Yeah. Yeah. So again, in this case with the obstacle, as you can see, it's not as obvious, right? First of all, because the agent was hitting a lot of obstacles and that kind of kept it away from going there, but also it becomes, it's much harder to make a decision. And in this case, actually doing only one iteration is not enough. As you can see, if I try to follow the policy at the start state, I will actually end up into the small cycle and never reach the goal, which is bad. But again, this is only one iteration. If we keep on doing this, this policy is already better than random. If we keep on iterating this, we should be able to actually find an optimal path from start to goal. Yeah. Okay. So I think for the second part, Feryal, do you think that we want to cover both Sarsa and Q-learning? Do you think we have the time to do both of them?
I think it's fine to cover, and maybe later on we're going to leave it for homework, the function.
Yeah. But of course, and this applies to all the exercises. I invite all of you to kind of play with these. These are all there, and you shouldn't just go and fill in the code for it to where the comment says code here, but rather even play with these things and either run it for multiple steps, change the step size to see whether changing the step size or having something adaptive works. It's interesting, and the visualization should help you understand whether what you're doing is on the right track, or even to understand the algorithms themselves. All right. So now I think we can go on and talk a bit more about the Sarsa agent. So Sarsa, basically, this is standing for it stands for state action, reward state action, which is what this algorithm kind of uses for its update. But you can think of this Sarsa algorithm as on-policy control. And what's different with these control algorithms, both Sarsa and Q-learning, which we will see later, and policy iteration, is that now we're trying to somehow do both the policy evaluation and the the greedy improvement at the same time, right? So once we do these things at the same time, it sounds a bit counterintuitive because you're saying to evaluate, I need a lot of samples. As you run your code up, we run it for 1,000 or 100,000 steps. But if you imagine you only run for 1 or 2 steps, that's not enough data to know exactly what whether or not the agent is doing the right thing. But basically, Sarsa and Q-learning are promising to do exactly that. It's saying, I don't care. I'm not going to wait to get 1,000 samples. I'm just going to update right away and see what happens. And it's the same with the greediness, right? It doesn't just say, oh, let me just finish to evaluate and do the greedy. I just do the greedy right away and see what happens. So it kind of combines the two to get a direct control algorithm that doesn't necessarily have to think too much about. And it makes it simpler because now we don't have to think about making this decision of how much should I run one versus the other. So now when we talk about, if you look at the pseudocode of Sarsa, what happens here, we have, when we pick the actions, we always use this notion of epsilon greedy. And this is very important to notice, because before we were just doing greedy, but now we're doing epsilon greedy. And why is it that we're doing epsilon greedy? Is very much related to what I was mentioning before when it comes to exploration, right? So Sarsa is an algorithm that is on policy, right? Which means it uses the same behavior and evaluation policy. And I think there was a question on why we don't have this here. And that's the idea. The way that the algorithm was designed is to say, we will have only one policy, and this policy will both collect the data and also will be evaluated as we go along. And if we stick with greedy, it's very easy for you to fail in terms of like getting to converge to a policy that's really bad, right? You can think of some very bad scenario, even the initial policy that takes you all the way to the wall, and then you just get stuck on the wall because you're trying to bump on the wall forever. But also, even if you start with a random policy, it's very easy to get stuck into a case where the greedy policy does a back and forth, and basically you will never get any good data. So because of that, we do a slight variation of it, and the idea is to do epsilon greedy, right? And the idea with epsilon greedy, we have it as a first coding task, is to sometimes, do greedy and sometimes be random, right? And the epsilon, this is a value that says, how often am I being random? So in this case, the default value for epsilon is 0.1, which means in that particular case, it means 10% of the times that I'm asked for an action, I will just return something random, and 90% of the time, I will actually look at the Q values and do exactly what the Q values are telling me is best. So that's basically the idea behind this policy. So once you have this implemented, think of this as a slight variation on the Y-liner that you had before for greedy. Now you have to do like two different cases and try to use the epsilon to decide. And once you have that, then you have to implement Sarsa. And again, if you look at the skeleton, it's pretty much the same as the skeleton for the evaluation. It's just that now we will do something slightly different, right? With the updates will be, this interaction, this notion of behavior, evaluation, policies kind of combined together. And now you kind of have to do them all at the same time. Makes for a much simpler algorithm, and also an algorithm where you just let it run, and you don't have to. There is no idea of iterations. You just keep on interacting with the environment until you stop and you say, "I'm done," which is very much in accordance with what we would want whenever we evaluate our agents, because most of the time what we want to evaluate them on is really on the sample complexity of performance, but of course we want to know some performance, how much data it required to actually achieve that. So in this case, because it's an online algorithm, we just let it run for a bunch of episodes, and we can evaluate it every time step and say, oh yes, this is the quality of the policy up until now. So I'll leave some time to let you actually implement this. Now, hopefully you'll be much more comfortable doing this, given that you've implemented policy evaluation. So I'll switch back to the chat just to see if there's any burning questions. Maybe Feryal, if you noticed any questions that I should address quicker than others, it would be good.
Oh, sorry. Do you hear me, Gheorghe?
No, I wasn't. You were muted.
Oh, sorry. Yeah, I was. So I was just saying there's a question on what is the difference between behavior policy and evaluated policy.
Oh yeah. Okay. So yeah, I can go back to that. So as I mentioned, for the Sarsa agent that should be what we're looking at right now, or maybe you should be working on, it's the same. So the evaluation and the behavior policy are the same, and what it is, it's an epsilon greedy with respect to the Q values that the agent is trying to compute. In the case of the policy evaluation, I can go back to that and maybe talk a bit more and clear up that confusion. Where is it? So if we look back at this diagram for policy iteration, I mentioned the fact that this iteration, it really talks about the iteration over the policies. We start with a random policy or any policy that you give your best guess at what the solution should be. And we iterate, we slowly improve this policy. And the way we slowly improve this policy is by evaluating it, right? So now we need both a behavior policy, and which is different from this policy that we're trying to evaluate, just to make sure that the policy that is being evaluated is not too bad at collecting data. Because the way to evaluate a policy is to collect data, to collect these trajectories that are listed here with tau. And we want to make sure that those trajectories cover the entire state space and not just some part of the state space that the evaluation policy somehow could get you stuck into, right? And particularly here, we talk about doing grid improvement, and grid improvement will make it deterministic. So it's very likely that at some point in this iteration, the policy that you're evaluating might actually go back and forth between two states because it doesn't know better. And we want to avoid that. And the way to avoid that is to make sure that we collect data with a behavior policy that it's different. In this case, random. I think we only use random for now. Yeah. And to address a bit the question on epsilon greedy, yes, so when we talk about epsilon greedy, you want to be, most of the cases, in most cases, you want to be greedy and less random, especially because the two things are kind of combined, right? So if you talk about the evaluation policy and the greedy policy being combined, now what we're saying is that the evaluation policy, which is the policy that we want to use, right, that we want to kind of iterate over, this has to be good, fairly good, right? But not deterministic, or too greedy, because if it's too greedy, then it doesn't do the exploration. So we wanted to do some exploration while also making sure that its quality is not too bad. And the best way to do that is to make sure that you use an epsilon which is not too large, right? 0.1 is what people commonly use. Even 0.05 is even better depending on the. But this is a hyperparameter, right? So for this agent, or you can do some annealing as well, even with the epsilon, where in the beginning you're more exploratory and then you slowly start to do it less and less. But for this case, we can just keep it constant to something like 0.1.
There is another question which is interesting. It talks about what if we don't know the reward function? What if we don't get any rewards? So that's really cool, and that's one area of research as well, when you call it no reward learning or task agnostic or something. And then sort of the reward notion can change. You don't have to get external rewards from the environment to be able to sort of learn a behavior. You could have intrinsic motivations, right? Some notion of curiosity that you can enable your agents with, and then it wants to seek to do very different things or reach states that are very novel. And actually some people argue that sort of this way of unsupervised or task agnostic training can help with downstream task behavior as well. So you first learn about your environment by just being curious, trying many things, and then sort of get some sense of the dynamics of the environment and the interactions. And then you can, after sort of you have that base policy, then you can fine tune on a given task that has a specific external reward function. So that's one idea.
Yeah, it's an excellent question, and thank you, Feryal, for the great feedback into other kinds of research. But I will also want to add the fact that in this case it's a small grid wall, but you could have it the case where unknown can be replaced with sparse, and sparse it's equivalent to unknown. So what sparse means, it means that it's super rare. So you actually, even to get the slightest reward, you actually have to be at least at least some level of goodness at the task. Imagine a robot that has to walk, right? So if I only give it the reward once it reaches it walks 5 meters, then that's equivalent to unknown reward. And in that case, you do need intrinsic motivation. You do need to maybe look at demonstrations. You have to the agent has to come up with its own reward function to even get unstuck and do some kind of learning, because in that case you get nothing, right? Yeah. So it's good to keep that in mind, and then to understand that even if, let's say, DMN always provides the reward because that's how the interface is designed, it will in some cases just send you zeros all the time, almost all the time. So you want to address that case as well.
A great point. And then that's where maybe demonstrations would be helpful as well, that you can put into your replay if you have access to experts, or there are some powerful ideas such as like hindsight experience replay that you can look at, that you can even learn from your failed sort of attempts at learning. Maybe you end up somewhere else in the grid world or in the environment, and you can relabel your even intentions and say, oh, I wanted to go there, and now I'm going to learn something about it. But these are, we can link to many of these papers in the chat later that are interesting. Great. Should we show the solution?
Yeah, we'll go slowly over the solutions. So again, going back to the greedy, the way we prove this is to, do an argmax whenever epsilon is less than your random. So you pick a random number between 0 and 1. And if the number is larger than epsilon, then you just are greedy. And if the number is smaller, then you basically just do randint over the number of actions, right? So in this case, the number of actions is really just the length of your Q values table. Okay, so this is basically the policy. And then for the Sarsa agent, going back to the solution, what we're doing, different from the policy evaluation. Again, if you look at the construction time, there's no behavior and evaluation. It's really just an epsilon, because the evaluation is constantly changing. The agent basically is in control of the evaluation policy. And what is that evaluation policy? Is basically just epsilon greedy with respect to the Q values, the latest version of its Q values. Right, so if we do the Q on the observation, which in this case is just an index, remember we're still in the tabular case, we get a vector of a length number of actions. We can just do epsilon greedy on that. Okay, and now for observe, it's very, very similar to what we will do for evaluation. I think actually the computation of the TD error is pretty much the same, right? If I'm not mistaken, probably the solution is almost the same. I can't even see the difference right now. But essentially, very similar thing. We do the TD error, and we use the step size to basically change the Q value with respect to what the TD error is telling us. Yeah, and basically...
Sorry, there is one question just before we move on. Can you quickly say how Sarsa differs from the previous agent you showed?
Yeah, so I think the way in which it differs, the main one is the fact that the policy that it evaluates is epsilon greedy with respect to its Q values, right? So essentially the evaluation and the improvement are happening at the same time. The previous agent, if you look at it, there's an evaluation policy which never changes. There's a behavior policy which never changes, at least whenever we run an episode. The only thing that changes is your estimates of the Q values. So it's really just trying to see how good is a policy if I don't change it, and I always use the same policy. Versus Sarsa, which says I have a policy, it's never the same, I constantly change it. And why do I constantly change it? Because I constantly change my Q values. So because I constantly change my Q values, epsilon greedy on those Q values will constantly change. But the theory and the people who came up with the algorithm made sure that if we do something like this, at least in the tabular case, we are guaranteed to actually reach the same optimal policy as if we were doing policy iteration or some other algorithm that looks for the optimal policy. So yeah, I hope that answers the question. Yes, there's also a technical question that says, why are we updating self.action in observe? So this is really up to you. But the way that most Acme actors interact with the environments is that they have this distinction between observe and update, even though you could maybe do them at the same time. But because it's a different function call, you want to make sure that updates knows which action to update whenever it does an update, right? So we save the action, as well as we actually even save the state and the action, right? And also we save the next state so that we know for the next update what the state should be, right? So that's kind of like a small technical detail where we want to make sure that we update the right entry in the Q table. And to make that correct, we have to save these values somewhere inside observe so that they're available when we update. But just always recall, you can look back at the run loop or the evaluation loop. What happens is always observe followed by an update function call. Yeah. So there's a question on covering how to use Acme and DMN. We're basically doing that online as we go. So I think if you're still a bit confused on what is expected, so we're not going to cover Acme entirely because Acme it has quite a lot of things. It's a bunch of tools and it covers a lot of things. But the only thing that we care about in Acme right now is the Acme actor. But we will see later, I'm sorry, I'll take that back. Later in the tutorial, we'll see how we can actually use Acme agents that have been already implemented at Acme to actually just modify or even run them on any environment, right? So the point is just for yourself to get comfortable with the way in which these agents work, just in case you want to use already a very, like DQN is a complex agent that you don't want to implement right away, or if you want, it's a very ambitious exercise. But those agents have already been implemented in Acme, so you might want to use it. And there's other tools, and there's maybe Feryal, you want to talk more, and you have some resources for them if they want to look more into Acme. But
yeah, of course. So in Acme, we have provided a tutorial of, like, for instance, using a D4PG agent, which is a continuous control agent, again, value-based, that you can follow. I've linked to it below. At the end of the tutorial, you can see. But also, I'm going to show you later, if the time permits, or if not, you can look at it yourself, that we are using a DQN agent of Acme directly to interact with this grid word, for instance. And why DMN again is needed in this case is just a choice. It's not necessary. It's just Acme agents that are already implemented expects an interface to the environment that is similar to sort of DM environment interface. And you will see even for the GIM environment that I'm going to show you later, which is a card pool, I'm wrapping this environment into a DM env environment. And that way it allows me to sort of connect it to an Acme agent without any problems. We can also offline describe more details in the Rocket chat after the session.
Yeah, so let's quickly try to run this on the my Colab is kind of slow right now. Let's run the implementation and maybe run it for 10,000 steps on the obstacle environment. Yeah, so as you can see, we run it for 10,000 steps, and the agent manages to get some kind of nice pattern on the value function. But if you look at the policy itself, you see that somehow it has this, it didn't necessarily evaluate properly this small shortcut from start to goal. Didn't get enough experience. We did epsilon greedy, but maybe the epsilon was too low. We could try to increase the epsilon and do some annealing. But essentially, we didn't necessarily give it enough chance to explore this path enough to be convinced that it's optimal. So, I mean, if only we could change one simple location, the policy in one single state, that we would probably have the optimal policy. But still, the agent manages to get a solution that goes around the obstacle the long way, right? Which is success in itself.
That's absolutely correct. And also one thing to add, just to connect with what Diana showed you with the cliff example, right? Here, Sarsa is on policy, right? So because the policy that it is using to behave is a little bit, greedy with this exploration term. So it is more conservative because it doesn't want to sort of hit into the walls to get these negative rewards. And that's why it sort of goes and takes the longest path in a sense, because it wants to avoid getting negative rewards as it's on policy. And maybe with Q learning, we will see that it discovers the shortest path if possible. I don't know if the parameters are going to converge, but we will see.
Yeah. Just so you know, what we visualize here is actually we ignore the epsilon. So the epsilon grid is important as we learn, but once you're done, you can forget about the epsilon, right? At some point when you try to just have the final result, that's when you say, well, I'm done learning, so let me just be greedy, fully greedy. And that's what we illustrate here, right? Just so you know that this is not taking epsilon grid into account. But again, it's important, and choosing the right epsilon value is playing with that, or even the step sizes might actually be something that will help you get the optimal path even with Sarsa. Okay, so now let's move on into Q-learning, which is probably one of the most famous RL algorithms, and very, very easy to implement, super easy, and that's why a lot of people actually like it, because it's super convenient, and it's always a very simple baseline to have. It's not guaranteed to always work, but it's simple to actually try out. So what's the difference now? What do we do next? We change the on policy to off policy control, right? So what does it mean that we do off policy? It means we do something very similar to Sarsa, where the evaluation is kind of combined with the greediness. But this algorithm basically tells us that we could actually come back and have a behavior policy, right? We can change the update in such a way that we can use any behavior policy, right? Whether it's epsilon greedy or not epsilon greedy or something else. And the Q value is guaranteed to converge, similar to Sarsa, to something that gives you the optimal policy. So it's called off policy control in this case because you are using any policy whatsoever. You can use data coming from humans playing the game, or you can have it from other agents that are very good at exploring the state space. And essentially, you learn the policy that is best at maximizing the reward, right? That's why it's called off policy. You're evaluating the optimal policy while executing a different policy, right? And the way to do this is to basically change the update. And instead of looking at the evaluation policy, instead of thinking of what would I do, what would be epsilon greedy here or there, we just take the max. We'll look at the Q values that we have, we'll look at the best estimate that we have, and we say, give me the max over those things, right? And this matches the idea of the optimal Bellman equation. The optimal Bellman equation is a way to describe the optimal policy, and that the optimal Bellman equation basically prescribes us and tells us to do the max over the Q value. So again, very similar to Sarsa. If you just take your Sarsa agent, copy paste it into the, well, not the whole thing, because the initialization is different, but try to take the observe and the update functions and just fiddle around and figure out what the change should be to get the Q-learning, then you should have a quick solutions to this agent as well. And again, we're kind of going back to this idea of being able to use a behavior policy that is different from the evaluation, but in this case, the evaluation is always fixed. It's the optimal policy, right? We evaluate the optimal policy, and the behavior policy could be anything. We could do epsilon greedy here as well if you really want to, but we could stay random. So in this case, we have a lot more freedom in Q-learning to say, oh, well, I can be more lenient with my epsilon because the update itself will guarantee to evaluate the optimal policy and not this weird epsilon greedy version of the policy that I'm using right now. So I don't know if there's...
There are some questions, but I feel like our amazing TAs are answering all of them in a great way. So I think maybe from now on, we sort of take less questions, but we will, after the chat, after the session, we will go back and answer anything that is left unanswered for sure.
Yeah, so there's a very good question on this idea of basically, observing, but somehow giving back control to the environment. So like the environment runs longer, and this is a very good question, and it goes into something that you'll see later with DQN, and also with a lot of complex agents, where you make the distinction between actors and learners. Right now, we kind of combine the two. So the idea is that whenever you observe something, you quickly store it somewhere in a replay buffer. You just send the data somewhere. You're just saying, oh, this is what the environment told me. Send it somewhere. And then you have another process that runs in parallel. And that process itself at its own pace can just collect the data and somehow look at the data and do a lot more work than something that blocks, for example, as something that is blocking as the way that we run it here. So that's something really interesting, and if you want to look more into it, it's something that definitely something that we exploit a lot at DeepMind. Like, for example, we do a lot of our algorithms will run a lot of actors in parallel and a single learner or multiple learners for different things that have to be learned. And why? Because for the actors, it's very simple. Tell me what you've seen. I'll pack it, send it quickly to some service that stores that data, and then the learners can collectively take everything that comes from many actors and do some learning and use like very complex models to do the gradient descent updates or whatnot.
Yeah, and one thing to add, and so you're not scared, so for instance, Acme is exactly used the way that Gheorghe was described. So the agent would look very similar, except that the actor would be split from the learner. So select action, observe first, these are going to be in the actor, and then the update function is going to be in the learner. And yeah, but the API looks very, very similar. So all the distributed learning is like handled by a module that queries them. Yeah.
Yeah, so now I think I talked a lot about the difference between Sarsa and policy iteration, but now because we talk again about the behavior policy, it creates a confusion. It says, oh, well, how is Q-learning different from policy iteration? So Q-learning is similar to policy iteration in the sense that it can use any behavior policy to do the evaluation, but it's similar to Sarsa in the sense that it combines, it doesn't have this, like the policy that is being evaluated, it's always the optimal policy. Right? Whereas policy iteration, it has a policy that it slowly changes as it goes along, and it always evaluates the best version of the policy that it has, right? So that's basically the idea. So Q-learning is similar to Sarsa in the sense that it doesn't have to think about this dual world where, oh, I have to schedule things and try to do an evaluation, then an improvement, an evaluation, then an improvement. No, it's all done at the same time. It's just that Q-learning says, I'm going to evaluate right away the optimal policy. I don't know what it is, but I do know that it should follow the Bellman optimality equation. So I will use that to do my updates, right? I hope that answers your question. I don't know, Feryal, if you have anything to add on that, because I think it's an important
yeah. I think it was clear to me, but hopefully it's clear to everyone, or we will explain more.
Okay, so as I mentioned, the solution shouldn't be too complex. So I'm just going to go through it and just mention that, again, it's very, very similar to Sarsa. But just to point out the distinction that I just explained in code, when we select action, we're no longer doing epsilon greedy. We're just using the behavior policy, whatever that is. Could be epsilon greedy, but it doesn't have to. And then essentially, when we do the TD-error, now we're no longer taking an action, right? There is no evaluation policy or epsilon greedy that tells us what the next action is. We are just taking the max, essentially. And that's how we computed the TD-error. That's the TD-error corresponding to the optimal policy. And then the update is exact same implementation, right? And this gives you essentially Q-learning. Okay? So again, the things that you play with this, you know, if you look at the implementation, even the epsilon, right, for the behavior, the only thing that you have to think about is the behavior policy. But remember that unlike Sarsa, you can be more lenient with this. Like the behavior policy, you can have so much flexibility with it. You don't have to get stuck with epsilon greedy. You don't have to worry about it because you're not doing on-policy updates. You're just evaluating the optimal policy as you go. So that's that's the power of Q-learning. So now I think we're running the Q-learning agent on obstacle. And as you can see here, we set the epsilon to 1. What does it mean? That's equivalent to random, right? We're saying we're always random in the behavior policy, right? But as promised, this agent, the Q-learning agent, even if you're always random with your behavior policy, it's able to actually learn even the shortcut policy, right? Unlike Sarsa, which had to be on policy, and we're always worried about this notion of like, are we collecting the right data or not, when we had to play with epsilon. But here, even an epsilon of equal to 1 will give you the optimal policy in the same amount of, in the same number of steps. So then we'll leave this as a homework, but the idea is that you could take this and try to play around and see what happens when you change the epsilons, and maybe make get to the conclusions yourself on whether or not this is important and what it does, at least for this environment. But remember that again, we worked on the grid world, but if ever you have another environment in mind which is not a grid world, or you want to change this grid world and create one where you think the task is even more challenging by setting up different number of obstacles, feel free to play with this. If you look at the code, it should be quite well documented and should allow you to play with this as much as you want. So there was this additional exercise, which I think we will leave it as a homework. The idea here is to use the idea of an experience replay. And this goes along the lines of what I mentioned earlier, where when we have the data, we don't just update right away from that piece of data. We do the same updates, but we will store it. And then we store lots of data, and that data stays there. And basically that would allow us to do more updates if we want, right? We can do updates. We can, if we store 1,000 of these transitions, then we don't have to just wait for the next thing that the environment tells us. We can just look back what happened in the past and reuse those interactions to do an update, sorry, not an update, but a lot more updates at the same time. So that's the idea of an experience replay. And essentially you will see the impact that it has, particularly on the data, on the sample complexity. So just maybe the same number of updates, but the number of interactions with the environment is drastically reduced, which is what this is really there for. But again, we'll leave it as a homework. We'll be there on Monday to talk more about, it's Monday, right? The homework session. We'll be there to answer questions, and the TAs are doing a wonderful job to help you right now and probably in the future as well when you work on this homework. So I'll give it back to Feryal, who will talk about function approximation now. Unless there are some questions, do we want to address any more burning questions before we move?
Yeah, I think while I'm presenting, maybe you can check the record.
Okay, perfect.
Did you find any questions? Because we are moving to functional approximation, if you have any sort of contributions.
One interesting question you might want to talk about is what's the difference? How is Q-learning different from doing epsilon greedy with the epsilon 0? Right. So I think this is important. It's a very good question. And the difference is when we do the update, when we compute a TD error, we behave as if epsilon is equal to 0. Sorry, now we pretend epsilon is 0. But we're still in Q-learning, even though we do that, we never use epsilon greedy with epsilon 0 to behave, right? We still use the behavior policy that is given and it's exploratory. So in a way, we're allowed to be greedy when we do the update, but to be exploratory when we collect the data. Yeah.
Yeah, very good point. Okay, so let's dive into part 2, which is on functional approximation. So we showed you in our simple environment how sort of tabular methods are very good at learning even the optimal policy, which was going through the narrow path. However, this is not going to hold true for very complex environments. Why is that? Even if in this simple grid world environment, if you change the goal location, then what happens is that you have to keep these Q tables for all versions of the positions of the goal and for each action, right? So it's gonna explode in sort of in memory, like how big this table is gonna be. And this is just even for this simple grid world, which maybe you can get away with it even if you enumerate all goal positions. But imagine for something like Atari, where sort of your state is dependent on each pixel value, then sort of the state space is huge and you can't really keep a table around to query for these cases. And in real world, it's even worse because it's going to be continuous a state space. Like imagine a robot that is in the environment, and you have to have the whole universe sort of modeled in your Q table, which is not possible. So you want some notion of transfer generalization. If you see some states before, you want to be able to generalize to slightly similar ones. And that's why function approximation sort of plays a role here. And in order to first start closer to what we learned on Q learning that Gheorghe just mentioned, we are going to go talk about neural fitted Q iteration. This was sort of a work by Martin Riedmüller in 2005, and we sort of modernized it a little bit here. But I'm going to walk you through so we understand how it's related. So it's a Q learning method where we are using a neural network to represent our Q function, basically. And this was one of the first papers to demonstrate how to leverage sort of neural networks for Q learning. We represent this Q function as a neural network, which sort of given an state, it wants to output for us the Q values for all possible actions. And basically, when we talk about function approximation and learning through these neural networks, we are talking about the loss function to optimize. By the way, Gheorghe, please interrupt me whenever you want, because I might leave some things out and it's important for everyone to learn. So please feel free to interrupt. So basically here we're going to talk about a loss function. And turns out that we can just use our TD error that was introduced before as a loss function here that is going to be minimized for us to satisfy Bellman equation. And there's a lot of text here. I sort of encourage you to go through it at your own pace. But here, I think you're familiar for L2 loss, for instance, from your computer vision tutorial that you had. So we can basically use something like that to optimize the Bellman equation, the TD error. And then this NFQ builds exactly on this Q learning. The only difference here is that first of all, the Q values are not a table, it's a function, and you have a random policy that sort of goes around, collects data. And then in NFQ paper, explicitly, they have a policy, behavior policy, that collects a lot of data. They use a data set, sort of they keep it in a data set similar to supervised learning, let's say, and then do a batch update on all of this data. And they use RMProp or something. So this is very interesting because it's very close to, let's say, offline learning, offline reinforcement learning, which is where you don't actually interact with the environment while you're doing reinforcement learning. You just have a data set that was previously collected by another agent, or you get it from somewhere, and then you want to still use reinforcement learning to learn from that. So here the version that we implemented is sort of more closer to a DQN, where sort of the agent is epsilon greedy. I have a version where the epsilon is, you can set epsilon to 1. And if you set that epsilon to 1, it turns to be exactly like NFQ because the agent is random and doesn't get updated. So we can play with both later, I will show you. Just one note, if you read this paper, and I fully recommend you reading it, they talk about costs to minimize instead of rewards to maximize. This is just a negative sign, so it's the same notions. So if you're maximizing reward, it's like minimizing the cost, basically. And I think I covered everything. Is there any questions, Gheorghe? Yeah, perfect. Okay.
There were some other questions related to the previous part, but I think here we're fine.
Okay, perfect. So as Gheorghe just mentioned before, we are talking about a replay. Replay is an excellent way of decorrelating the experience. Let's say when you're on policy, sort of when you're updating, it's all correlated, your samples that you're updating. When you have a replay buffer, you can just dump all the data there, maybe throughout the whole experience of the agent during training. And then while you're updating, you just sample a mini batch and sort of try to update. And that's very powerful. And here in NFQ, as I mentioned, they have a data set that is fixed, is not getting updated throughout learning. The version that we are looking at is we are adding to this data set as we go forward. Great. And yeah. So let's go to the coding task. So there is a class we implemented for you. It's a neural fitted Q agent. This is very similar to what you saw before, so it shouldn't be surprising. This inherits from Acme actors, so it needs functions such as select action. We also have the Q values as mentioned before. We introduce a loss, which is the TD error that we want to optimize. And we have the train step and update function. And the observe and observe first is also the same. So just 1 second before going deeper, so the replay buffer is just basically a storage for you to add experiences to. In the previous version that Gheorghe mentioned, it's just a list that you can append to, a state, action, next state, and rewards. And that can work. It's just, it might explode in memory if you keep adding, to this list. So we are borrowing this very simple replay buffer class from RLAX. RLAX is a library for reinforcement learning in JAX that was released, I think, I don't know, a few months ago. And this it is very nice because you can, I'm copying that code here, but normally you should just import it. I just wanted to show you how it is. But it gives you like sort of building blocks of building a reinforcement learning agent in JAX. And for instance, the losses, the TD, I don't know, the epsilon greedy, all of this is implemented for you and you just use it. Of course, for this tutorial, it's really important that you implement these yourself. So to understand sort of how the theory connects to code. But later on, when you are sort of familiar with these things, I really recommend not reinventing the wheel every time you write an agent because it's prone to sort of making mistakes. And these libraries are there to support you for that. Great. So, yeah, Gheorghe, do you think I need to give more maybe information here about the agent before we go to the solution, the task, or should we just dive in and answer questions as they come?
I think that we can just dive in. I mean, there might be questions that come up in terms of like what kind of stuff which they should use, but again, like try to switch. I would suggest for students to try to switch their mindset from NumPy now to JAX and JNP because now we want to do AutoDiff. Do we have that part or not? Do we ask them to implement the gradients or?
Yes. So we have first of all, we have the TD error that they need to implement. The training step here,
Yeah.
you need to sort of, we put some hints for you. There are some libraries that make your life, some functions that make your life easier. For instance, JAX does value and grad that just does, a forward and also computes the gradients. And then optics is sort of your optimizer. And we have introduced all of these here. Sort of you have your optimizer, which is Atom, and then you initialize the parameters of your optimizer. You also want to initialize the parameters of your network. Yes, they're missing, so it gives you a nice idea of, like, I'm sure you have seen it in the previous tutorials where you initialize the parameters using Haiku, because we are using Haiku as the neural network library. And if not, we can show you later in the solution. And then sort of we keep all the parameters in this nice sort of training state name tuple to make this clean. It's a parameter, this is optimizer state and the step of the training. In policy, we want you to write what the action should be, basically what is the output of this, which is epsilon greedy, and you can actually use RLAX epsilon greedy instead of optimizing yourself because you've done it once before, so you already know how to do it. And let me check. This is the Q values here. As mentioned, you're not querying a table. Instead, you're actually doing a forward pass of your Q network, given the observations. Yeah, I'm adding a batch dimension here because this network expects to receive a batch, but you don't need to worry about it. And then the loss is, again, for a single transition, you need to implement it. And let me see if I need to give you more details. But everything should be very similar to the previous sort of Q learning method that Gheorghe showed. It's just more, as he said, you're not in NumPy word, you're in JAX word. And yeah. Gheorghe, do you want to add anything?
No, it's fine.
Okay, so we give maybe 5 minutes. I don't know how much time we have. Yeah, I think 5 minutes should be fine.
Yeah.
and we will answer questions in Rocket Chat. Great, I see there are some recommendation of resources. If you go down later in the tutorial, we also added some of our favorites. There are so many of them. Spinning Up is great. I've used it myself before, and it's TensorFlow. I think there's a PyTorch implementation as well. And I just want to reinforce what Diana was mentioning, that it's really important before sort of getting into very complex agents and sort of implementing to understand the theory well. And I think these tabular methods really give you a way of sort of understanding exactly what is going on. And really, before sort of diving down into complex, I don't know, Rainbow or like Impala or like other very complicated agents, definitely try to grasp these basics and play with this collab with the tabular agents, and then more simpler function approximation to get the idea, and yeah, and then move forward. Did we answer this question? If Q-learning is able to retrieve the optimal policy, even the behavior policy is totally random, why one would choose a behavior policy which is epsilon green? How the performance is affected in an off-policy setting if I keep exploring too much? I think I'm going to answer partially, and then Gheorghe can take it. Let me check. There are two parts to this question, so I'm going to answer the first part. Yeah, that's a very good question. So sometimes when the state space is huge, random policy is not definitely able to cover the whole state space, right? I mean, if we could cover the whole state space, it would be amazing. I mean, we just randomly, with a random policy, we would go everywhere, and then that gives us actually the optimal policy. But the problem is that that's not really the case. Yeah, and sometimes you really want to either have some intrinsic motivation or something that takes you where it's novel, so you don't end up exploring the same state many times, and make sure to cover all the state space that is new to you, so to get the most amount of information. Yeah, and sometimes, I don't know, Gheorghe, do you want to add to that?
I think Piotr had a nice back and forth on this. I was
perfect. Sorry,
and there was even very good additional resources.
Perfect. That's amazing. Sorry, I missed. It's very hard for me to follow Rocket Chat back and forth. It comes up very weirdly in my. But thank you so much for all the TAs that are answering. This is really helpful.
Thank you.
And one thing I wanted to add, I think this question came up early on in a slide or something for Diana or Doina, I don't remember, but it was why reinforcement learning has not been sort of has crazy sort of improvements, such as like computer vision or language modeling and stuff like that. And I think one thing that is really powerful, and one thing that was really powerful in the past years, I guess, with computer vision, language modeling, is the huge data sets and sort of these huge models that learn from these data sets. And in reinforcement learning, because this is an active learning framework, you know, like you want to interact with the environment, get some experiences and learn from it, you can't really leverage huge data sets. Of course, in DQN, and then we have these huge replays, we can leverage these data sets, but our methods sort of relies on interacting with the environment. But again, I want to iterate that, for instance, in the case of NFQ, you don't necessarily need to interact with the environment. while you're learning. And this field is called offline reinforcement learning. And it has a lot of sort of recent improvements in that area. Even somebody used the whole experiences of an just a DQN agent, and showed that if you just learn from the experiences of this DQN agent, you can go beyond that DQN agent optimal policies. So it's really empowering to look at this area of research, and hopefully it's going to have similar sort of progress as computer vision and language modeling in the future. Perfect. So in the interest of time, I'm going to go to the solution. I forgot what we left out. So I think just to look, we have the policy that is a epsilon greedy policy. So basically, we query the Q values for this observation and given the parameters of our network. And then we receive an actions given our lax of epsilon greedy function that is nicely implemented for us. We sample, given the Q values, the epsilon greedy action, and then we return these actions. Then I think we had this implemented for the loss. Okay, this is very close to what Gheorghe showed you before. Just one important note is that here for TD error, we are putting a stop gradient on the target Q values. So this is the target value where we have the reward plus the discount times the Q of next state, basically maximum action that we showed before. But here we are querying again the Q network for A, and these are all, this target is going to be frozen and no gradients will be passed here, because then it makes learning very unstable, because you're changing your targets as you're updating your state action Q function. And yeah, it's just one note that it's good to put subgradients here. And we are really looking into updating SA rather than, ST+1. And I think what else did we add? These are all very similar to what we saw before. And
okay, it's a train step that we might want to cover.
Oh, that's true. Okay, perfect. Yeah, and here, as we said, we are using Jack's value and grad. We are passing the loss to get the loss and grad function, and then we apply that to our parameters with the transitions that we have. These transitions come from sort of sampling a batch from the replay memory, and then we get the gradients, and the loss is returned to us. And then we want to apply these updates to our parameters using the optimizer that is add-on here. You could use any optimizer you want. And then you get the new state of the optimizer. These are all functional due to Jack's being functional. So there is no state in the optimizer. We always need to keep it around. And then we get the new parameters by applying the updates that we got from our optimizer to these parameters. And then we update our state of our training by putting the parameters here. And yeah, and the update is calling the train step. And in update, basically, we are sampling transitions from our replay buffer, given the batch size that we specify. And then, yeah, and then call the training state basically with the transition and the current state of our parameters that we mentioned. Just one quick note here. We are calling this agent NFQ, but this is not necessarily NFQ exactly. In NFQ, there is one batch, so they gather the whole data and then do one update on this whole batch. And one actually interesting things that DQN introduced was the concept of mini batches, that you sort of sample small batches and update, do stochastic updates rather than just one update. So although we are currently NFQ, it's not. It's just closer to modernized version of Q learning. And yeah, I hope this is clear, but we definitely can answer more questions. I'm gonna go ahead and run this. And now we're gonna look at the behavior. So I'm gonna first put epsilon equals to 1. This means that the behavior policy is always random. It's not getting improved. And this is closer to what NFQ did initially in the paper. Perfect. So one thing I wanna show you is that how we build this Q network, because we need a neural network to pass to the neural fitted Q agent. This Q network, we are building it using the Haiku sequential module. There are many ways to build neural networks in JAX. Haiku is, we just wanted to be consistent, and sequential just simplifies if you have a sequential network, but you could also implement a Haiku module here and build a more complicated network. And there is a tutorial in Haiku, also a collab, I believe. I can send it into Rocket Chat later. Basically, this is a very simple network. It's like 2-layer MLP, yeah. And then also we are here using the simple grid word task. One thing I need to tell you is that if you remember in Q learning tabular version, we were using the state index because we wanted to enumerate all the states. Here, our neural networks, we could pass it the state index, it's fine. But just to make it more interesting, we are passing it agent and goal position index, like XY of goal and XY of the agent concatenated together. And later we are going to change that to the full grid for DQN to show that this can scale, these neural networks can scale to more complex observation spaces where tabular cannot. And yeah, and we are learning. So here you see that episode return is not good. This is because our policy is random. Obviously, there is no learning for the policy behavior policy itself, but the loss is going down. And that's the loss, the TD loss that we're talking about. And I think this is a slow because the episode length is always very long because the random policy, of course, doesn't see much reward and the episode doesn't terminate fast. But when we change the epsilon, then you see that as the agent learns, the episode terminates much faster and the whole learning is way faster. I hope I haven't put a lot of episodes. I have, so 300, we have to wait for 300 episodes. But it's already learned, so the loss is going down, and this loss, I think, corresponds to a reasonable behavior.
I think while we wait, it's just wanted to add that one of the things that it's nice about doing something like NFQ or DQN, which is left for the probably is left as a homework, is that now we move away from agents like Q-learning that have one parameter, like the step size, to something where you're in control of a network. Like now you can play around with the network and figure out like, oh, maybe something that I've learned in supervised learning or unsupervised learning will help in building better representations. We use the optics, right? Now we say it's not just an update with a step size. Now we use optimization packages that allow us to do some more advanced way of keeping track of these updates. So using JAX or deep reinforcement learning in general, it opens the door to so many more options and so many things to try out that you want to do it. It's not just a convenience because the state space it scales better, but it just allows it to be more flexible, and it opens up the door for many more things than just thinking about the math of the RL problem itself, and that's why it's super 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 interesting. I think you're muted.
Yeah, there's a very good question. What is this dummy observation thing? I'm really sorry I didn't explain this part. Let me go. Hi. Great. So when we want to initialize our network, we sort of need to initialize these parameters, and we need to know the shape of the observation and sort of everything that is expected. And that's why when we want to initialize, we could either sample a data set if we have some data in the replay already, which we usually don't if you're just starting with a training with empty replay. So what we do is there is an observation spec that is passed to this agent, and Acme agents usually require that. And we constructed it here. Yeah, I think we constructed it here, exactly. So we have the environment spec. Our setup environment gives us the spec. This is usually the wrapper of any environment that you have, can give you the spec of the environment. Basically, it tells it what is the shape of the observation, what is the shape of the actions, and that helps you construct your network and not hard code these things. You could also hard code, basically, but we don't want to. And then here, when we initialize, we just generate a random dummy observation, which follows the same shape, but it's not anything. It's just zeros or ones or whatever. And then we initialize the parameters of our network using the init function in Haiku to basically initialize the whole network that we are going to be updating later. And yeah, that's it. Okay, let's see if our agent is learning. It is learning, but it's slow. So I'm going to go a little bit down just to tell you about DQN. So what you saw there was NFQ is simpler version of Q learning with function approximation. Here, DQN was sort of the first time that actually these methods were applied to very complex settings. So as you can see in DQN, the observation is no longer, state features. It's actually an image pixel observations of the game. This was very powerful because we saw that actually these methods can generalize to much more complex domains than previously done. And we use convolutions with DQN, and our networks is more complicated, but it's basically the same thing that we saw before. So we have some observation, we pass it to the network, and it gives us the Q values of different actions. And I think DQN introduced a few other sort of improvements over the previous works that we mentioned, and Diana also brought up. For instance, we have now a replay buffer in DQN, and we sample mini batches from this. This is very helps with the stabilization of learning. We have a target Q network, and for constructing the regress. What we are regressing to, so we are not updating that too fast. So our targets are constantly changing, and that also stabilized the training. There are many these small things that help the QN sort of scale. But I guess it started from, trying to make Q learning work for Atari, and they had to introduce a lot of important sort of stabilization techniques to make that happen. Let me check. We are getting there, 60 more episodes. Okay. Okay, I'm going to go down and just show you how you can create an Acme DQN agent. So we have a homework for you to actually implement the whole DQN agent yourself using what we taught you before, and it should be possible. And we have a solution as well in case you're wondering. But given these libraries such as Acme, you can just use an existing DQN agent for your given problem. Here we just build a grid word task, and then we can construct our network. As I mentioned, we want to use convolution, let's say in DQN. In our case, we can create, for the observation of the grid, we can ask for the grid instead of the state index or the XY position that we were using before. We are actually querying the grid, which is height, width of the grid times different channels. Here, channels describe, one is for agent position, one is for walls, and one is for goal. And we can pass this through convolutions. And and then this is simple two-layer NLP afterwards. And then we can simply ask, so I imported DQN from Acme, so we can just ask Acme, we want to use your DQN agent, and this is the environment spec. So Acme expects you to give it an environment spec, and this is why I was talking about DMN wrapper, because DMN wrapper can wrap your environment and give you exactly this environment specs that Acme agents expect. And then you pass the network, you give the batch size. There are many parameters that you can go have a look. Samples per insert and epsilon and mean replay size, for instance, how big you want your replay to be before doing the first update, how much data you want it to be there. Because sometimes you don't want to start updating off the bat because your policy is random and you want to gather more data so you can sort of have a meaningful update. And let me check if our agent is, so our agent is finished. We can now evaluate our agent. So it is successful. every time, and this is no no wonder this is a very simple task. But as you start making this task much more complicated, it has more difficulties compared to DQN. For instance, if you use pixel observation or huge action spaces. But in this simple case, this is actually very, very good method to use. And then we can visualize again the learned Q values as we've done for tabular agents. We see that, yeah, it learns something reasonable, maybe not too reasonable, but it knows that the value of going down when it's in these areas is much higher, which means that it wants to go to the goal. And then we can compare the greedy policy versus the behavior policy. And this is the same. So one thing I recommend to you is go and here where so when we are setting the epsilon, play with the epsilon, make the epsilon be very small, and then you can see the agent actually doesn't learn anything because the behavior policy is like too conservative and it doesn't see the state space, and then what is it going to learn from, right? And it never sees the reward. So then you will see that this agent cannot learn at all. Okay, now we're going to go to Acme DQN agent. So as I mentioned, we can instantiate the DQN agent that way. So I'm going to just create the environment, build the network. Perfect. And then run the training loop with this agent that came from Acme for our problem. And I think we have 3 minutes, so I'm not going to talk more about this. Just you will follow the same thing. You can visualize the Q values. You can compare your greedy policy with the agent policy later. And yeah, we have some coding tasks for you here. We describe sort of what DQN algorithm does and the update functions that are very close to what we described before. So you should definitely have a look. And then we are talking about how these implementations are done. For instance, we can use WQ learning or Huber laws, and they're easy and hard tasks for you to implement. And we provided the solution as well. Yeah, and then one thing that I recommend is that, we just showed the grid board and it looks all simple and nice, but what happens if the environment changes? You can see here, nothing happens, it actually works. So you can just, if you wrap the environment and observation correctly, you shouldn't worry about anything. And that's the power of these neural network approaches, right? You don't need to think about, oh, I have to engineer some features now, there's a new problem. No, it's just works. So of course you have to do some hyperparameter tuning and stuff, but you can just see that you can apply the same DQN network to the problem. And yeah, and I'm just using this gym wrapper from Acme, which wraps any gym environment that you give it into a DM environment wrapper. And that sort of helps with if you want to use Acme agent, but you can just use your own agent and you don't need to worry about these things. And then you can visualize the training curve. We just show you how the reward is changing according to throughout training. And just to show you, we also have some resources that you can have a look. Of course, there are many more tutorials and blog posts and code out there. These are just some of our recommendations. Yeah, perfect. Gheorghe, do you want to add some things to conclude?
No, I think you covered pretty well. So yeah, the DQN task is it was intended to be left for last because we expected that it might have to be done as a homework. But I think it's a super interesting exercise to do because this is what gets publicized, and this is something that, it's a good exercise into grabbing a paper and understanding the complexities that it takes to actually build the agents. And I think what we try to do with this part is to kind of force you to adapt the things that you've seen earlier in the tutorial to something that uses the same thing. Like, how can you take the TD-error and try to understand how that TD-error interacts with a more complex agent like DQN? And hopefully you will get that. As I mentioned earlier, feel free to try it. It's a challenging task. It's not something that we expect you to do, but as you run into it, and if you have questions, reach out to us, to the TAs, and we'll be there on Monday to address more questions online.
And shout out to our TAs, like they were amazing. Yes. Really made our life much simpler. Thank you so much.
Yeah.
So see you on Monday.
Yes, thank you.
Thank you. Bye.
Bye.